Hello everyone, welcome back to the course Introduction to Infrastructure Asset Management. This course is offered under MOOCs, an initiative of Government of India. In the last week, we started our discussion around a generic infrastructure asset management process. We saw that the process includes multiple steps starting from data collection to monitoring. The last week was focused on data collection. We discussed different aspects of data collection. We talked about how to handle missing data, how to collect data, and so on. In this week, the focus will be on the next step, which is performance modeling. So, here I will be discussing about performance modeling. Week 4, this is the first lecture where the concept of performance modeling will be discussed. This is part of the decision framework which we started in the last week. My name is Chirag Kothari. I am an assistant professor in the Department of Civil Engineering. So, before we start discussing performance modeling, let us revisit the definition of performance. What is infrastructure performance? Infrastructure performance is given as follows. The performance of an infrastructure system can be defined as the degree to which the infrastructure system serves its users and fulfills its purpose for which it was built. The performance is measured by the quality of service as well as the length of service it provides. So, if you see, there are few key words here. Performance is basically defined as a degree to how well an infrastructure system serves its users, and also we try to assess whether it fulfills its purpose. The way we talk about it is given as the quality of service as well as the length of service. Now, having discussed what is infrastructure performance, the question is, what is failure? An infrastructure system is considered to be failed if it is unable to perform according to the criteria which is expected, or if it does not meet the desired level of performance. So, till now we have been discussing this fact that performance varies like this. Now, say there is a critical limit and we do not want the performance to go below this particular limit. So, an infrastructure can be considered to be failed if the performance goes below this particular line. So, this area here is basically the place where the infrastructure has failed. We have also discussed that failures can be due to various reasons. An infrastructure can fail due to functional reason. We saw in the example of bridge that it was taking a lot of time to move from place A to place B. It was not performing as expected. Now, this is a functional failure. The structure is still sound. It is still safe. However, it is not meeting its requirement as per functionality. So, this is a functional failure. Second, there could be a structural failure. This is if the structure has failed. Third could be a safety issue. Say a particular infrastructure system is no more safe. It could be because of any reasons. Then it could be considered as a failed infrastructure. Having discussed infrastructure performance, now let us discuss what is performance modeling for an infrastructure. The goal of performance modeling is as follows. Here we are trying to develop representations of the physical asset. So, you have a physical infrastructure, we have an understanding that its performance will vary over time. Now, when we are doing performance modeling, we are trying to develop a representation of this. We want to develop this representation so that it can be used for decision making. Here, what we are trying to do is, we are first assessing the condition, and using that we are trying to predict asset's behavior. Now, we are using this information to provide early warnings for potential failures, and based on this information, we try to optimize maintenance strategies and conduct resource allocation. So, the goal of performance modeling is that for any infrastructure, you want to understand what is the current performance. You want to understand how the asset is behaving. Then you want to have any early warnings. So if you feel that the infrastructure might fail, you want to determine those warnings, and you want to use this information to plan your maintenance strategies. We already know that infrastructure's performance varies on several factors. Some of these include age, usage patterns, the environmental conditions, and the maintenance practices. Moreover, an infrastructure consists of multiple components, and each of these components can perform differently. So, performance modeling for the entire infrastructure systems is complicated. For example, let's go back to our example of bridge. A bridge will have a superstructure, it will have a substructure, it will have columns, piers, joints, foundations, so on. Each of these infrastructure components can be of different materials, different types. They might deteriorate at different levels. So, this makes performance modeling difficult because there are multiple interacting components which come together to define performance of an asset. Moving on, in the last week, we had seen that there are different types of data which is collected. There, I had talked about collecting relevant data to model assumptions. Here, we had discussed that if we want to predict the performance of an infrastructure asset, we need to model some of the assumptions. This particular lecture will be focusing completely on this. We had seen that there is a lot of data which can be collected to predict performance of an infrastructure asset. We had seen that age, the technology of construction, weather conditions, occupancy levels, frequency of maintenance, any physical damages, the building material used, and the current exposure to natural and man-made calamities can impact the performance of an asset. We had also talked about other aspects around biodeterioration, chemical attacks, integrity of the structure, also the strategy of planning which was used for construction, and the effectiveness of asset management. In the last week, we had seen that we need to collect relevant information about all this. Now, in this particular class, we will be looking into how do we use this information to finally predict the performance of an infrastructure. A lot of data can be collected, but now how do we process this to finally predict performance of an infrastructure asset? In order to model systems performance, we first try to understand how an asset is deteriorating. Deterioration basically means that performance is expected to go down with time. In case of deterioration, we are basically saying that an infrastructure asset will deteriorate with time or usage. Moreover, different components of the structure can deteriorate at different rates. So, for example, if you see this bridge here, there are different components. There is a deck, superstructure, then there are columns, piers, guardrails, so on. Each of these can actually deteriorate at different rates. For an infrastructure, we can have multiple performance curves depending on the criteria which we have in mind. So, when we try to do this, it basically boils down to three aspects. First, we try to determine what are the existing defects in the asset. Then, we try to understand what is the severity of these defects. And finally, we try to understand how critical are these effects to the overall performance. So, for any performance modeling, we try to understand what are the existing defects, what is the severity of these defects, and finally, what is the criticality of these defects. Once we have this information, we move to the next step of performance modeling. Let us discuss how can we go about doing performance modeling. There are different performance curves which can be used to determine a system's performance. Here, I will talk about one of them, which is a sigmoidal performance curve. A sigmoidal performance curve looks something like this. Here, there are different parameters Pn is the performance of the infrastructure at year n. Pi is the performance at year n minus 1. N is the age of infrastructure. Now, if you see, there are three parameters: alpha, rho and beta. Alpha basically controls the maximum performance lost. I will talk about this with an example so that it becomes clear. Rho talks about the inflection point. It controls the inflection point. And beta controls the shape of the middle of this curve. To understand this better, let us see an example. On the x-axis here, I have age of the infrastructure. On the y-axis, I have performance. Say the initial performance is 100. So, performance at time t equals to 0 will be 100. That is the maximum performance. Now, performance is expected to deteriorate with time. If you see here, there are three curves here. Basically, I have varied this parameter beta. So, if you see here, the blue line is beta equals to 1.5 and the gray line is beta equals 2.5. So, we see that by varying beta, we can get different performance curves. At the same time, I can vary alpha as well as rho. Let us see how varying these impacts the performance curve. The goal of performance modeling is to make an estimation of these three parameters so that the model which we get is a good representative of the infrastructure asset under consideration. Before we talk about how to determine these parameters, let us try to understand these parameters in detail. To understand these parameters, I have set up an Excel model to mimic this particular equation. If you see here, the way performance at each year is calculated is using the sigmoidal equation. We have already seen the equation is given as follows: Pn is equals to Pi minus alpha times e raised to the power minus of rho divided by n raised to the power beta. So, if you see here, for case 1, performance at year 1 is given as follows: the performance at year 0 minus alpha, which is 5, multiplied by e raised to the power of minus of rho divided by n, which is year here, raised to the power of beta. And I have calculated performance up to year 30. So, if you see here, for case 1, the performance starts to deteriorate after year 6 and it goes down till 63 at the year 30. Now, if you have a look at these three cases, beta is varying, where we have beta of 1.5, beta of 2 and beta of 2.5. So, if you see here, a shorter beta means the infrastructure is expected to deteriorate faster. I hope this concept is clear, because at any particular time, say at year 20, if I see the performance using blue line, the performance is 90. However, the performance using orange line is higher than 90. The gray line is even higher. So, a smaller beta means that the performance of an infrastructure asset is expected to deteriorate quickly. Now, let us see other parameters. Here, I have kept alpha as 5. What happens if I change this alpha? So, say instead of 5, I change it to 7. Please follow the blue line. Now, if you see here, on changing alpha from 5 to 7, you will see that the shape of performance curve has changed. A higher alpha means the infrastructure is deteriorating at a faster rate. Now, what happens if I change the beta from 1.5 to 0.5? The moment I do that, you will see that the shape of the curve has changed. It is expected to deteriorate a lot faster. So, alpha is controlling the maximum performance lost. If you see here, at alpha equals to 5 for all these three cases, the maximum performance lost up to year 30 was somewhere here above 60. But if I choose a higher alpha, the performance lost increases. The more I increase it, the performance goes further down. Beta is basically controlling the shape of the middle of the curve. So, this particular shape here is controlled by beta. A smaller beta is almost making it as a straight line. A slightly higher beta makes it relatively curved, and a higher beta means that the infrastructure's performance is deteriorating slowly. Now, what about rho? Rho controls the inflection point. Here, rho is set at 20. If I change it to 10, if you see here, the inflection point is moved here. If I change it to 15, the inflection point is somewhere here. If I change it to 18, or let's change it to 20, the inflection point is further here. Say I change it to 25, the inflection point will further shift. So, basically rho is determining the inflection point. If you want to see it through numbers, we can see that if I have a rho of 20, the asset starts to deteriorate from year 7 onwards. But if I have a rho of 10, the asset actually starts to deteriorate from year 3 onwards. A higher rho basically means that the asset will not deteriorate up to year 10. So, depending on the type of infrastructure, if it starts to deteriorate quickly, then we should have a lower rho. However, if there is an infrastructure which is expected to deteriorate only after say year 10 or year 20, then we can actually have a much higher rho which represents this case. So, I hope the idea of these three parameters and what they represent is clear. We have seen that performance of an infrastructure asset can be represented using a sigmoidal curve. We also discussed a sigmoidal curve has three parameters: alpha, beta and rho. Now, the most important question in performance modeling is how to determine these parameters. We need to determine these parameters in such a way that they are representative of the physical asset under consideration. Let us discuss what are the different ways to do it. The question is, how do I determine equation parameters? I want to estimate performance at year n. For that, I need the value of alpha, the value of beta as well as the value of rho. N is the age of the infrastructure. Now, how do I determine this? There are different ways to do it. I will just give a brief overview about them. The first option is we use physical models for deterioration, that is mechanistic modeling. Here we try to understand the science behind why performance is going down, and we try to create some physical models. For example, when we will discuss concrete structures, we will discuss how to model corrosion. There are some physical models which can be used to do this. So, the first option is to do physical modeling, a more mechanistic modeling. Option 2 is you use subjective judgment. Since there are different components in an infrastructure, each component is expected to deteriorate at different rates. Sometimes it gets difficult to create mechanistic model for all of them, and we have to rely on subjective modeling. This is because oftentimes we do not have the relevant data for how the infrastructure has performed over time. If we have a lot of data available, then instead of using subjective modeling, we can actually use empirical modeling. In case of empirical modeling, we use past performance data to predict these parameters. So, say I have a lot of information where Pn is known at different years. Now, I can use this information to predict alpha, beta and rho. For example, let me go back to my Excel sheet. Say, for a given infrastructure, we have this information available with us. That is, at year 0, the performance was 100, at year 4, the performance was 99.99, and at year 30, performance was 63. Now, if you have collected information over years, you can actually use this information to predict what will be alpha, beta and rho for that particular equation. This is known as empirical modeling. A common method used here is maximum likelihood estimation. This particular lecture will not go into details of how to conduct maximum likelihood estimation. There is a lot of literature available around this. I'll just talk about what is MLE or maximum likelihood estimation. In addition to these three options, fourth option is to use a hybrid method, combination of above. This is what is done in the field. For some of the parameters, we use physical models. For some of the parameters where performance data is available, we use empirical models. And for others, we use subjective judgment. We combine all these together to create a hybrid method for predicting performance. Let us talk about option 3 in detail. Option 3 is to use past performance data. Here we try to employ maximum likelihood estimation. MLE is a statistical method which is used for estimating parameters. In case of a sigmoidal curve, which we had talked about, we saw there are 3 parameters. The goal is to find the values of these parameters such that the observed data becomes most likely. So, say we have information for 50 years about an asset. We know how its performance is varying over time. Now, in order to estimate performance for year 51, we first want to estimate the 3 parameters, and then the moment we do that, we will have an equation which is y is equals to f of x, such that we can predict what will be the performance at year 51. So, we use MLE to find these parameters. These parameters are found in such a manner that the distribution which we have, that is y is equals to f of x, should best fit the observed data. The idea here is that an infrastructure, if it has performed in the last 50 years, most likely it will follow that trend in future as well. Now, maximum likelihood estimation is a very broad topic. There are both analytical solutions or numerical solutions to solve and find values of these parameters. Any statistical book or course would talk about this in detail. In this lecture or this course, we will not go into details of these. It is important to know that there are these methods which can be used to determine parameters of different equations. In this particular lecture, we started our discussion around the concept of performance. Then we talked about the need for performance modeling. Then we saw a sigmoidal performance curve can be used to model performance. We talked about how to estimate parameters for such a curve. Now, before I end this lecture, I want to talk about some of the advancements in performance modeling. Over years, there are new methods which have come up which help in performance modeling. One of them is integration of IoT, Internet of Things, for data collection. So now we have a situation where there are sensors installed in an infrastructure asset at the time of construction, or these sensors are installed after construction. They are used to collect different information, and this information is transferred to a model so that we have a more real time information. The information is actually stored in the form of a digital twin. So, we have some real dashboards. These dashboards, when connected with IoT systems, have real time information about the asset. They can be used for visualization of performance. Another advancement in this field is around using BIM, Building Information Modeling, for asset management. Building information modeling is another aspect where all the information about an asset is stored in one common platform. It is especially useful during the design and construction phase. It has a lot of potential to be used for asset management phase as well. BIM actually provides as a feeder to the digital twin model. In addition to IoT, digital twins and BIM, we also have a lot of research going on in using machine learning, AI, deep learning and so on for pattern recognition and for prediction. So, IoT is used for data collection. BIM and digital twins are used for data storage, and there are advancements around machine learning and AI which are used for data processing to predict performance. So, you try to recognize different patterns and try to predict performance. So, these are some of the advancements which are coming on in the field of performance modeling. With that, some of the important references around this topic. So, I will end my lecture here. Thank you. Thanks for listening.